Namaskaram. Today we are going to start the Fourier series. Fourier series is an infinite series that represent a periodic function in terms of sine and cosines. And the Fourier series is the starting point of Fourier analysis. In Fourier analysis, another one means one extension of Fourier series is Fourier transform. So Fourier analysis involves Fourier series, Fourier transform, and the discrete version of Fourier transform. For example, discrete Fourier transform and first Fourier transform, everything. Okay, and this Fourier analysis has several applications, especially in signal processing. Okay, so first we are going to define periodic function. A function f of x is called a periodic function if f of x plus t equal to f of x for a positive number t. Okay, if there exists a positive number t satisfying this condition, then we can say that f of x is periodic. For example, you consider f of x is equal to sin x, and we know that f of x plus 2 pi is equal to sin x plus 2 pi, and also we know that this is equal to sin x. So here f of x plus 2 pi equal to f of x. Clear? So, and we know that 2 pi is positive. So in this case, this is our t. So if there exists a t satisfying this condition, then we can say that it's a periodic function. So sin x is a periodic function. Okay. Similarly, you consider f of x plus 4 pi. That's equal to sin of x plus 4 pi, and we know that sin x plus 4 pi is same as sin x. This is equal to our f of x. So in this case, this also t. So this t is not unique for a periodic function. Clear? So the smallest such t is defined as fundamental period of a periodic function. Clear? So in the case of sin x, which is the fundamental period? Yes, the smallest such t satisfying this condition is 2 pi in the case of sin x. So fundamental period of sin x is 2 pi. Okay. Okay, next definition is piecewise continuous. A function f of x is said to be piecewise continuous on an interval if it is continuous everywhere on this interval except at a finite number of jump discontinuity. For example, you consider this function in the interval ab, and it is clear that this function is continuous in the, suppose this value is some x naught, then it is, okay, one second, suppose this is x naught, then it is clear that in the interval a to x naught it is continuous, and in the other interval, that is x naught to b, this function is continuous. So at x naught it is clear that this function has a discontinuity, and this continuity is a jump discontinuity. So what is the meaning of jump discontinuity? Jump discontinuity means its left hand limit and right hand limit both exist and finite. Okay, in this case, this is the left hand limit value and this is the right hand limit value, and both exist and finite. Okay, so a function is said to be piecewise continuous. The function has maximum finite number of jump discontinuities. Okay. Okay, for example, suppose a function is continuous in the interval ab, then it is, of course, it is piecewise continuous. Why? It has no jump discontinuity. That means number of jump discontinuity is 0. Okay, it is finite. Okay, so that's the idea. Okay, now we are ready to define a Fourier series. If f of x is a periodic function with the period 12 in the interval c to c plus 12, we consider only an interval of length period. Okay, length of this interval is 12. Satisfying the Dirichlet's conditions. The Dirichlet's conditions are, the first one, f of x is piecewise continuous. We know what is piecewise continuous. Okay, and second one is f of x has finite number of maxima and minima. These two conditions are called Dirichlet's conditions. So a periodic function satisfying these two conditions, then we can define the Fourier series of this function, given function f of x. How? This is the Fourier series of given function. A naught plus sigma n equal to 1 to infinity n cos n pi x by l plus bn sin n pi x by l. This infinite series is defined as the Fourier series of this function f of x, and we denote this Fourier series by s of x. Clear? Okay, now in this expansion, a naught, ans and bns are unknown, and this a naught, ans and bns are given by these three formulas. So a naught is equal to 1 by 2L integral c to c plus 2L f of x dx, and an's are given by 1 by L integral c to c plus 2L f of x cos n pi x by L dx, and bn is equal to 1 by L integral c to c plus 2L f of x sin n pi x by L dx. Okay, and these three formulas are called Euler's formula. These three formulas together are called Euler's formula. Okay. Okay. So this is the Fourier series of this function f of x, and we denote this Fourier series by s of x. So naturally there is a question, what is the relation between f of x and s of x? Okay. So answer is given by the next result. Okay. So the relation between f of x and s of x. So this is our Fourier series of this function and denoted by s of x. Then these are the relations. The case 1. Suppose f of x is continuous. Suppose f of x is continuous at a point x. For example, you consider this function in the interval c to c plus 2L, and you think about a point here, x is here. Then it is clear that at this point our function is continuous. There is no break. So you evaluate s of x. S of x means the value of this Fourier series at this point. Okay, and this result says that that value is same as f of x. That means this height. Okay, then we have one more case. Suppose there is a discontinuous point. Okay, so in this example, suppose x is here. Then we can evaluate s of x. S of x means value of the Fourier series at this point. And what about this one? Then this theoretically it says that the value of the Fourier series at this point equal to f of x plus f of x minus by 2. That means average of the left hand limit and right hand limit. Okay, in this example, what is left hand limit? Left hand limit means this value. This is actually f of x minus, right? And similarly, what is the right hand limit at x? Actually here the right hand limit means this height. Okay, this height is right hand limit. So you find f of x plus and f of x minus and take the average. That is the value of the Fourier series at this point. Okay, so this is the relation between f of x and s of x. If it is continuous, they are same. The Fourier series same as function. Otherwise, the Fourier series is equal to average of the right and left limit. Okay, these two limits exist because we know all the discontinuities are jump discontinuities. Okay. Okay, next we consider a special case, that is 2L equal to 2 pi and c equal to minus pi. So when c equal to minus pi means what about the starting point? Oh, this is our 0. The starting point is minus pi, right? And our endpoint is endpoint is c plus 2L. So here c is minus pi, and what is 2L? That is 2 pi. So endpoint is pi. So interval is like this, minus pi to plus pi. Okay, suppose a function is defined in this interval minus pi to plus pi. Then what are the analogous changes in Fourier series and its coefficients a0, an and bn? Actually, our Fourier series in the interval c to c plus 2L is a0 plus like this. So what about the series? a0 plus sigma n equal to 1 to infinity an cos n pi x by L, that is n pi x by L. What is L? In this case, in our now we assume that 2L is equal to 2 pi, right? So L equal to pi. So this is pi. So you can cancel these two. So this term become cos nx. Similarly, this is bn sin n pi x by pi. So you can cancel. So this is sin n pi, sin nx. Okay. And what is the analogous changes in a0, an and bn? Our a0 become 1 by a0 equal to 1 by 2 pi integral c to c plus 2L. Instead of c to c plus 2L, our interval is minus pi to plus pi. So minus pi to plus pi f of x dx. And what about an? An is equal to 1 by L. What is L? L is pi. 1 by pi integral minus pi to plus pi f of x cos n pi x by L. In this case, our L equal to pi. So this become cos nx. So f of x cos nx dx. And similarly, what is bn? Bn is 1 by pi minus pi to plus pi f of x sin this is pi, so you can cancel sin nx dx. These are the corresponding changes when we assume that 2L is equal to 2 pi and C equal to minus pi. So our Fourier series is like this, and A0, An and Bns are given by analogous formulas. Okay. Okay, next we are going to analyze a problem related to this type of Fourier series. So find the Fourier series of f of x is equal to minus k if x is in between minus pi to 0 and k if x is between 0 to pi. Okay, anyway this function is defined in the interval minus pi to plus pi. We know that in the case of Fourier series we always assume that our function is periodic. Okay, and they given function in a particular period. So how to draw this function? Suppose k is somewhere here, k is positive. Then it is given that if x is in between minus pi to 0, then function value is minus k. If it is k, then minus k is somewhere here. So this is the function value. Okay, if x is greater than 0, if x is between 0 and pi, then function is throughout k. So this is the shape of the function. And we know that this function is periodic. So you can extend it. Suppose you consider another interval, pi to pi to 3 pi, that is another interval of length 2 pi. Okay, you can extend this function using the rule, using the property of periodicity, f of x plus 2 pi equal to f of x. Okay, so what is the value of the function in this interval, pi to 2 pi? The function in the interval pi to 2 pi is same as function in the minus pi to 0, because this function satisfies this condition, right? So the graph of the function is like this, so you can continue in all these directions. So actually this is the full function. Okay, anyway we are going to find the Fourier series of this function in this interval. After that we have to evaluate this infinite series, value of this infinite series, 1 minus 1 by 3 plus 1 by 5 minus plus etc. Okay, we know that the Fourier series in this interval is this one, and A0, An and Bns are given by this formula. So first we have to evaluate A0 and An and A0, An and Bn, okay, using these formulas. Then you have to substitute. So this is our A0. So our function has two values depending on the interval. So we have to split this integral as sum of two integrals. Clear? Like this, integral minus pi to 0, our function value is minus k. In this interval 0 to pi, our function value is k. Now we can easily integrate. So this is minus k into x minus pi to 0, and this is k into x 0 to pi. So if you substitute upper limit and lower limit, this become minus k 0 minus pi plus k times pi minus 0, and this is actually plus pi, and plus pi into this is 1 by 2 pi. Ultimately this become minus k pi, right? Minus k into plus pi, and plus this become k pi. So this term is 0. So A0 is 0. Okay, next we have to find An. N is given by this formula. So 1 by pi. As similar to the previous case, we have to split this integral as sum of 2, because f of x has two values. 1 by pi into minus pi to 0. In this interval function is minus k into cos n x dx plus integral 0 to pi k into cos n x dx. Now we can integrate this cos. So the integral of cos n x is sin n x by n. Then next we have to substitute the upper limit and lower limit. So this n is constant, so you can take outside. So minus k by n, sin 0 minus sin minus n pi. Okay, we know that these terms are all 0 because sin 0 equal to 0. What about sin minus theta? We know that sin minus theta equal to minus sin theta. So this become plus sin n pi. And what about sin n pi? Sin n pi equal to 0. So this term is also 0. And 0 and 0. So all the terms are 0. So all the ans are 0. Whatever be the n, all the ans are 0. So this bn is like this because function has two values. Then the integral of sin nx is minus cos nx by n. Okay, next you have to substitute the upper limit and lower limit. So after substituting the upper limit and lower limit, the terms are like this. And we know that this cos 0 is 1. And what about cos minus theta? That is equal to cos theta. So this is cos n pi. And what is cos n pi? that is minus 1 raised to n. Okay, so this term is 1 minus minus 1 raised to n. Similarly, this is minus 1 raised to n and this is 1. So this expression become, okay, this is like this. If you take a minus outside, this term become actually plus k by n 1 minus minus 1 raised to n, right? Now this k by n, now these two terms are same, k by n into 1 minus minus 1 raised to n, and this also plus k by n into 1 minus minus 1 raised to n. So you can add these two, so 2 times. So this become, yes, so this is our bn. So that is 2k by n pi into 1 minus minus 1 raised to n. So a naught 0, ans are 0, bn's are given by this formula 2k by n pi 1 minus minus 1 raised to n. Now we can write the Fourier series. Okay, we know that this is the formula of Fourier series. So here a naught equal to 0 and ans are 0. So our Fourier series become sigma n equal to 1 to infinity 2k by n pi 1 minus minus 1 raised to n into sin nx. Okay, if you try to expand this Fourier series, what happened? When n equal to 1, what about this term? This is 1 minus minus 1 raised to 1, that is 1 minus minus 1, that is 1 plus 1, that is 2, right? Suppose this is corresponding to n equal to 1. Suppose n equal to 2, then what happened? This term is 1 minus minus 1 raised to 2, that is equal to 1 minus 1, that is equal to 0. So as a conclusion, if n is odd, this expression is 2. If n is even, this expression is 0. So if you expand this, then these terms contain only odd terms, the terms corresponding to odd ends. Okay, all others are 0. So when n equal to 1, 2k by pi, and this term is 2, 2 into sin x, plus when n equal to 2, the term is 0. When n equal to 3, 2k by 3 pi into 2, one more 2 is there, into sin 3x plus etc. Next term is 0, then etc. Okay, here this 4k by pi is common, you can take outside. So this series become 4k by pi into this term is sin x plus 1 by 3 sin 3x plus 1 by 5 sin 5x plus etc. So this is the Fourier series of this function. Okay, next we have to evaluate this infinite series from this Fourier series. Okay, next we have to evaluate this series from this infinite series. For which value of x gives almost a series like this? What's your decision? Suppose x equal to 0, then what happened? When x equal to 0, sin 0, everything is 0. Okay, so we have to find this series. So if you substitute x equal to pi by 2, then what happened? The right hand side become, or s of pi by 2, you think about s of pi by 2. What about s of pi by 2? That is equal to 4k by pi sin pi by 2. What is sin pi by 2? That is 1. We have a result sin 2n plus 1 pi by 2 equal to minus 1 raised to n. Okay, so what about sin 3 pi by 2? Sin 3 pi by 2 means sin 2 times 1 plus 1 pi by 2. So here n equal to 1. That means minus 1 raised to 1, that is equal to minus 1. Right. So this is 1 plus 1 by 3 into minus 1. Similarly, this is 1 by 5 into 1, etc. So s of pi by 2 is like this. So this is equal to 4k by pi 1 minus 1 by 3 plus 1 by 5 minus plus etc. So this is s of pi by 2. Then what is the relation between s of pi by 2 and f of pi by 2? F of pi by 2. Because it is clear that at pi by 2 our function is continuous, there is no break. So this s of pi by 2 f is same as f of pi by 2, right? So we can equate this infinite series as f of pi by 2, right? Because they are same, because the function is continuous. Then what is f of pi by 2? From this graph or this function, definition of function, it is clear that f of pi by 2 is k. When x equal to pi by 2, function value is k. So this is equal to k. So you can cancel one k, this is also k. So you can cancel this k, then you can easily find this value. So what is 1 minus 1 by 3 plus 1 by 5, 1 by 3 minus plus etc. That is equal to, we can cross multiply this 4 by pi to the right side. This is, now it is 1. Okay, you can cancel this k. So that is pi by 4. Right, you got it. So the sum of this infinite series, this alternate series, is equal to pi by 4. This is the one mathematical application of Fourier series. We can evaluate some complicated, we can evaluate the value of some complicated infinite series. Yes, so this is equal to pi by 4. Okay, in next session we will discuss more problems related to Fourier series. Okay, thank you.